Hey guys, I'm going to make an answer key, a video answer key for the AP Exam Review 2 homework. Okay, so I hope to get through it pretty quickly. Let me read this question for you, the first question. A grocery store purchases melons from two distributors, J and K. Distributor J provides melons from organic farms. The distribution of the diameters of the melons from distributor J is approximately normal, with mean of 133 millimeters and a standard deviation of 5. For a melon selected at random from distributor J, what's the probability that the melon will have a diameter greater than 137? Well, I would do this simply this way. I'm going to do it over here for you. It's normally distributed. We know that the mean is 133, and the standard deviation is 5. And we want to know what's the probability that the melon will have a diameter greater than 137. That's over here. So basically it's all that area. So if you go into your calculator, and this is normal distribution, so second var is the distribution, normal CDF. You put in the low, which is 137 to infinity. The mean is 133. The standard deviation is 5. So therefore we get 0.2119. So this first answer is 0.2119. I don't know if you could read that here. Okay, so that's for part A. Part B, there's another distributor. Distributor K provides melons from a non-organic farm. The probability is 0.8413 that a melon selected at random is from distributor K will have a diameter greater than 137. For all the melons at the grocery store, 70% are from J and 30% are from K. For a melon selected at random from the grocery store, what is the probability that the melon will have a diameter greater than 137? So here you need to make I would make a chart like this. So probability that the melon comes from J is 70%, probability from K is 30%. Now, if it comes from J, what we learned above was that if the probability that it's greater than 137 millimeters is 0.2119, and the probability that it's not greater is 0.7881, 1 minus that. And if we want to get the ends here, it would be 0.7 times 0.2119 is 0.1483. 0.7 times 0.7881 is 0.5517. Now let's go the K direction. If the probability that the melon comes from distributor K is 30%, and we learned in the problem over here, which said the probability that is 0.8413 that the melon is from distributor K. So there's a 30% chance that the melon came from distributor K, and a 0.8413 chance that it's greater than 137. Multiply 0.3 times that, and you get 0.2524. And 1 minus 0.8413 is 0.1587. So you multiply those two together, and you get 0.0476. So now the question is, we want to figure out what's the probability that the melon has a diameter greater than 137. So we go to the J, and greater than, it's 0.1483. That's this. And we go to the K, and greater than 137 millimeters, and that's 0.2524. Add those together, and you get the probability that the melon selected at random is greater than 137 millimeters is 0.4007. That's part B. Part C says, given that a melon selected at random from the grocery store has a diameter greater than 137 millimeters, what's the probability that the melon will be from distributor J? So this is a conditional probability. What's the probability that the melon will be from J, given that it's greater than 137? So if you remember conditional probability, at the top, the numerator is going to be the probability that it comes from J and is greater than 137. That's 0.1483. How do we get that number? We look at the tree diagram that we were just working with, if I can find it. Let's see, oh yeah. So 0.1483 is right here, that it comes from J and is greater than 137, over the probability that it's greater than 137, which is these two numbers. greater than is 0.1483, and greater than here is 0.2524. Add those together and you get this fraction, which turns out to be 0.3701. That's the probability that the melon comes from distributor J, given that we know already that its diameter is greater than 137 millimeters. All right, we're going to go on to question number 2. Question number 2 says a shopping mall has 3 automated teller machines, ATMs. Because the machines receive heavy use, they sometimes stop working and need to be repaired. Let the random variable x represent the number of ATMs that are working when the mall opens on a randomly selected day. Here's the distribution. The probability that 0 are working at the mall is 0.15. Exactly 1 is working is 0.21. 2 is working is 0.4. 3 is working is 0.24. Okay, what's the probability at least 1 is working? Let's go take a look at the answer key here. We would add up, at least 1 is not 0, so it's 1, 2, and 3. You'd add up the 0.21, 0.40, and 0.24 to get 0.85. Part B, it says, what's the expected number of ATMs that are working when the mall opens? Put these numbers in L1 and these numbers in L2. Go to your stat and one var stats. You're going to make sure you put L2 for your frequency, and that is going to become your expected value is 1.73 machines are working when the mall opens. Okay, here's a conditional probability. What's the probability that all 3 ATMs are working when the mall opens, given that at least 1 ATM is working? So let's look at that. So what's the probability that all 3 are working, given that at least 1 is working? So if you remember about conditional probability, it's the probability that both these things are true, that all 3 are working, given at least 1 is working. Well, that's actually just the probability that all 3 are working, 0.24, over the probability that at least 1 is working, and that we got from over here, 0.85. So 0.24 over 0.85 is 0.282. Okay, part D. Given that at least one ATM is working when the mall opens, would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected value from part B? Well, logically speaking, if we know at least 1 is working, and the expected value from part A actually includes that none are working, this should be higher. But if you want to prove it, you can actually do, which I did. I actually did this. I found the conditional probability that 2 work, given that at least 1 works. I did that conditional probability very similar to the way I did the conditional probability from part C. That turned out to be 0.471. I did what's the probability that 1 works given at least 1 works. I did the conditional probability of that, and I made a brand new table with the probabilities that 1 has to work, so therefore it's going to be 1, 2, or 3, and I put the probabilities that we found into the table, ran the statistics, one variable statistics, and we got the expected value is 1.965, which is definitely greater than 1.73. Okay, let's go on to problem number 3. Now, I want you to notice that in this particular problem, this tree diagram is a little different from the ones that we've done, and you have to be prepared to make some changes to what we learned, because they're not always going to be straightforward. So here's what the question says. I take a true-false test. I study for it and feel well prepared. I estimate that I have a 90% chance of knowing the answer and thus getting it correct. On questions I don't know, I'll guess. So since it's a true-false, you have a 50-50 chance of getting it correct. So there's a 90% chance I'll get the answer correct right off the bat. And then of the 10% that I don't know, half of them I'll get correct and half of them I'll get incorrect. So now, what's the probability that I get a question correct? So that's going to be correct here, which is 0.9 plus 0.05, 0.95. I'll write that here so you can see it a little larger. Part B, if I get a question correct, what's the probability that if I get a question correct? It's because I knew it. So here it's a conditional probability. What's the probability that we get a question correct because we knew? Let's make this C for correct and knew. Well, knew is the denominator, and we know, that the bottom is going to be that we got the question correct, which is the 0.95. And the numerator is that we got the question correct this way. 0.9 over 0.95 is 0.947. This one is, if I guess, this is a probability. The probability if I guess, then I get the problem correct is, let's see, 0.05, yes. So if I'm coming down this way, the probability I get the question correct, which is the probability of this, 0.05, over the probability that I'm guessing, which is this way, 0.1, there's a 50% chance that I get the problem correct if I guess, which makes sense because there's a 50-50 chance here. All right, let's take a look at the last problem. A writer has a bad habit of holding on to pens when they stop working. So he holds on to bad pens. He has 3 pens in his briefcase. The first pen has a chance of 80% of working. The second pen has a chance of 60%. The third pen has a chance of 40%. If the pen stops working, he'll try another pen. Draw a tree diagram to illustrate this problem. This tree diagram is kind of little. I think I might have another diagram of it. Let's see if I have a good one. Yes, I'll lay my good one over it. So if he picks the first pen, there's an 80% chance that it works. If he doesn't pick the first pen, right, the first pen doesn't work, then he's going to try the second pen, and there's a 60% chance that it works and a 40% chance that it doesn't work. So the chance that you go in this direction, it's 0.2 times 0.6 is 0.12. Now, if the second pen doesn't work, we have to go and try the third pen. There's a 40% chance that it works and a 60% chance that it doesn't work. So to find the probability at this end here, it's going to be 0.2 times 0.4 times 0.4 is 0.032. I'll write that a little bit bigger here. And if we go straight down this way, it's 0.2 times 0.4 times 0.6, which is 0.048. So this is our tree diagram. And again, it's not the usual tree diagram, which has constant branches off of each node. Here it ends, if you see what I mean. Okay, now based on this Venn diagram, let's answer the questions that we have here. Find the probability that at least one pen works. So there's an 80% chance that it works here. There's a 12% chance that it works here. And there is a 0.032 probability that it works here. So we would add these together, 0.8, 0.12, 0.032, all the branches where we find a pen that works, and that adds up to 0.952. Okay, part B, if the first pen doesn't work, one of the other pens will work. In other words, what's the probability that the second or third pen work, given that the first doesn't? I'll just put NW for not working. All right, so the denominator is going to be the first pen doesn't work, which is the 0.2, that's going to be in the bottom. And the probability of 2 or 3 is the probability that you have the second pen working and the first pen doesn't work, which is going to be 0.12. Or the third pen working when the first and the second don't work is 0.032. Add 0.12 and 0.032 to get 0.152. It's going to be 0.152 over 0.2, and that's 0.76. Okay, so that is the solutions for this homework. So please check your answers.